this year's Davis lecture. I'm Don Brenner, the department head of the Department of Material Science and Engineering here at NC State. So before I turn this over to Professor Tracy to introduce today's speaker, I want to acknowledge the person for whom this lecture is named for. So Bob Davis is up in front. Thank you, Bob, for your generosity to endow this and allow us to hold this lecture every year. We really appreciate it.
You are welcome.
Okay. Okay. Joe, I'm going to pass this over to you to introduce today's speaker.
Good afternoon. It's a pleasure to have Professor Moungi Bawendi here today. He received his bachelor's degree in 1982 from Harvard University and his PhD in 1988 from the University of Chicago. He then started his studies on nanomaterials during 2 years of postdoctoral research with Louis Bruce at Bell Laboratories. In 1990, Professor Bawendi joined the faculty at MIT, where he leads an interdisciplinary research program on the science and technology of chemically synthesized nanostructures. He's a pioneer in the field of colloidal quantum dots, and Professor Bawendi's groundbreaking work on methods for controlling the synthesis of quantum dots made it possible to better understand their physics. He and his students have co-founded several startup companies for applications in missive displays, biology, and medicine. Professor Bawendi is widely recognized for his research accomplishments, including membership in the U.S. National Academy of the Sciences and receiving the Nobel Prize in Chemistry in 2023, together with co-laureates Louis Bruce and Alexei Ekimov. I have the privilege of doing my PhD under Professor Bawendi's supervision. He deeply values curiosity-driven research and gives his students and postdocs tremendous freedom to explore interesting ideas. Let's give Professor Bawendi a warm welcome.
Thank you, Joe. Thank you, Don, for the invitation here. It's really my pleasure. Is this working? Can you hear me? Yeah. Okay. To be here to present this lecture. So what I'm going to talk to you about today is the origin story of this material, these colloidal quantum dot materials, and what we've done at MIT with them and where the field has ended up. It's a story of curiosity-driven research turning into a technology, innovation as a result of asking really fundamental questions, and then seeing where that leads you. My title keeps changing; it keeps getting shorter and shorter. This is actually the next to the last version. The version that I use now is from Curiosity to Technology, which says the same thing, but it's even shorter. So I haven't quite updated the title yet. Okay, so let me tell you about quantum dots first. So a quantum dot now it's working. Okay, so a quantum dot is a small particle of semiconductors containing hundreds of thousands of atoms. Semiconductors come in many, many different flavors. The one that you typically know about is silicon. The ones that we study are generally binary semiconductors that have two different kinds of elements. And the one that we study the most is made up of cadmium and selenium. So this is like a model of cadmium selenide quantum dot. And the part that makes it quantum is that if you put an electron, a free electron, in that small semiconductor particle, it obeys quantum size effects. So I'm going to tell you what that is. Now, how do we know, first of all, that we're making a quantum dot? A lot of the inventions and innovations come at a time or follow the technology that allows you to actually characterize and see that technology, that innovation, right? So there's usually a technology, a characterization technology that precedes the invention. And in this case, the technology that is super important is the electron microscope. Because we're looking at things that are a few nanometers in size. And we want to make them as perfect as we can. The best tool is actually to see it, right? Light microscope is not going to do it because the light wave is too long. So the ability to be able to, for the students to be able to go to an electron microscope, make new synthesis, go look at it, and come back and iterate, that is the part that has allowed the field to begin with and to grow. So electron microscopy, I think, is incredibly crucial for this field of nanoscience to know what we're seeing. And so when you do the chemistry right, then you see these little particles. They're all about the same size. In this case, they're all about 4 or 5 nanometers in size. And then you know that you've got a good sample. And then you can go back and optimize things or whatever. Okay, so that's the quantum dot. Now let's go to the quantum part. And for the quantum part, I want to take you back a little bit to some fundamental quantum mechanics. Because that's important to understand how a quantum dot works. So I've always been, I love quantum mechanics. It's my favorite course to teach. And the reason why I love it is because it's, it's magical. The effects are counterintuitive, they're weird, they're strange, and one of these strange things about quantum mechanics is that something like an electron that you can think of a particle can also behave as a wave. There's this particle-wave duality in quantum mechanics that is the reason why life exists in a sense. Why do molecules exist? It's because of the covalent bond. Why do covalent bonds exist? It's because of quantum mechanics. It's because of this particle-wave duality in nature. Why does a hydrogen molecule exist? If electrons were particles, they would never exist. Right? If it was just about electrostatic interactions, you'd have hydrogen atoms, and they would never form a molecule. So quantum mechanics is really important, and this particle-wave duality concept is super important. And there's an experiment that was done at Hitachi back in the late 1989 that illustrates this. And every time I look at this video, I can just my mind goes, because it captures this basic quantum mechanical phenomenon, which then we can understand, from that we can understand how quantum dots work. And so in this experiment, this is done in an electron microscope, very much like the one I showed you. So in this microscope, they put in a very thin filament, a charged filament, charged positive with a positive voltage on it, and then 2 plates. This whole thing is actually pretty small. The filament is much smaller than a human hair. And 2 plates, and then there's a source of electrons, an electron gun, basically. And this source of electrons can shoot out 1 electron at a time. So, poof, you get an electron coming out. You wait a few seconds, poof, another electron comes out. And then there are 2 identical paths that these single electrons can go through. And then it gets spread out on a scintillator plate with a camera below it. And then you see the electron appear, hits the energy gets given off as light, and you see little spots where that electron appears. And so when you think of this as, if you think of these as electrons as these little particles that are shooting out of the source and being detected as energetic particles in the scintillator, classically what you think might happen is that you would see the shadow of the wire, right? A rain of electrons, very light rain, one at a time, and this wire just shadows what comes on the other side. So let's do the experiment. So the experiment is this video here. Let's start the video. So now we see these single electrons come out. Looks pretty random. We think it's random because it's, the source electron might go one way or the other. It's pretty random. So, and the video is going to speed up and sort of give us a wider view, because otherwise the experiment, you can hear the whole hour looking at this video. We don't want to do that. And so so, it looks quite stochastic. The other part of quantum mechanics is that when you do an experiment, the result that comes out, if you're in a quantum mechanical regime, is stochastic. It's a probability of seeing the result. And so, maybe it's not that random. Maybe it's that stochastic effect of quantum mechanics that you see. You just have to do the experiment over and over again to get the average value of the result. And as we watch this apparently random pattern appear, suddenly we see that the pattern begins to emerge. So the position of hitting the single plate is not at all random. You see these stripes appear. It's not a shadow. What you see is an interference effect. You have these two paths, and that electron, after it leaves the electron gun and enters the apparatus, it's a macroscopic apparatus. It's huge compared to what we think of as the size of an electron. Right? We think of an electron as being femtometers in size. This apparatus is on the size of a human size here, and you can put it together as a human retriever. So it's behaving as a wave in that apparatus, very much like if you had water waves. I'm going to do this with my hand. If you had water waves hitting a pier that has two holes in it, coming out of the piers, you could have these hemispherical waves coming out, and then they would interact with each other. And far away from these two little holes that water was coming out, you'd see a series of waves that have a high peak in them, and no wave and a high peak. That's from the interference of the waves together. That pattern is exactly this pattern. But when you think of water waves, you think of a bunch of waves, like a trail of waves coming out, continuously hitting this thing. In this case here, we have a single electron coming out and hitting, choosing. We think of it, classically we think, okay, it has to choose one of the paths. But if it has to choose one of the paths, then it would be a shadow. It wouldn't be this interference pattern. So that single electron, as a wave, interferes with itself. That's mind-blowing, right? A particle interferes with itself, but there's the result. It creates this huge wave function, this huge wave that knows about the entire apparatus. An electron can be a huge wave. Okay. Particle wave level. Then it becomes a particle like that. Let's use that now to understand quantum dots. Okay, so again, let's go back to the particle version of an electron. We know that if you're in a big circuit, we have electrons that can carry electricity. They're particles moving through wires, but what happens if you take that electron and you stuff it in a nanobox, a little tiny box? The wave properties come out. It's no longer a particle. It no longer behaves as a particle. The box is small enough that the electron can't be thought of just whizzing around as a particle really fast in that box. It's now a wave that fills the entire box. Just like the electron in the previous experiment was a wave that filled the entire apparatus of these two paths and knew about the two paths. So now that electron knows the size of the box. It fills the box as a wave. So we know about waves and boxes, waves and cavities. We know that about sound waves. So if I look at a flute and I compare that to a piccolo, we know that the flute has a pitch which is deeper than a piccolo, and that all has to do with the size of the cavity. And I'm color coding it, with red as being deeper than blue, or lower energy than blue. We know that from organ pipes, the same thing in organ pipes. The little organ pipes, the cavity influences the pitch of the sound that comes out of it. And the same thing happens for an electron in this cavity. We take a bunch of these little boxes, these quantum dots, these semiconductor particles. But the first thing we have to do is we have to put a single electron in those boxes. There's already a lot of electrons in there because these boxes are not empty. They're full of atoms. And each atom of cadmium, for instance, has 212 electrons. That's a lot of electrons. But they're all tied up next to nuclei. They're not free to explore the entire box. They're not these single waves that we want to put in there. How do we do that? Well, we could try to put a circuit, a few wires, and try to put one electron in the box. That's kind of hard to do. Another way to do it is to use light. Use light and use the photon of the light to liberate one of the electrons next to an atom, liberate it out of where it's close to the atom, and fill the box. And to do that, we use blue light. And we can then create the single electron that is now liberated to fill the box. It's very much like another way that you know about is strings and guitar strings, let's say. So unless you do something, that guitar string doesn't really do anything. In order for you to hear sound from the guitar, you have to strike the string. You have to pluck the string. You're taking energy, creating the wave on the string, and that wave on the string then translates into the sound wave. Right? So we strike the electrons here, we create the electron wave, and eventually that electron wave finds where it used to be. There's now a hole left behind next to the atom where it used to be. And the energy is of that electron wave when it finds where it should be, is translated into a photon. So we go from blue light, we create these single electron waves that have different energies. The short wave has a higher energy than the big wave. This is kind of like the pitch of the sound, high pitch, low pitch. And when the electron finds the hole, it creates light, and then you can see it in fluorescence. And so these vials have the same material, different sizes, and the light that it emits depends on the size of the wave. You can go from blue to red or green to red. That's the quantum size effect, or the particle in a box effect, for those of you who are more physics inclined, taking freshman chemistry. It's a very simple effect, and so when I was a graduate student, spent a summer at Bell Labs and with Bruce, and I saw this idea for the first time. I fell in love with it because it's so simple, and it captures the magic of quantum mechanics so nicely. When I was a graduate student, I studied first. I was a theoretical polymer physicist, doing statistical mechanics. Then I transitioned to be, as a graduate student, to be an experimentalist looking at the vibrational properties of very small atoms. I thought maybe polymers were too big, so I went to the other extreme. One of the molecules that I studied was H3+, 2 electrons and 3 protons. You can't get any smaller as a polyatomic molecule. It's the smallest polyatomic molecule. And I loved it because the quantum mechanics of how that molecule vibrates and everything like this, you can really understand it at a very fundamental level. And I just loved it. But this is even more simple. This is really, you're seeing quantum mechanics. Okay, so now we go to the discovery of the effect, and then my contribution, which was the synthesis. So the discovery of the effect was by Lou Bruce and Alexei Ekimov. Alexei Ekimov was working in the Soviet Union in the late 70s, early 80s, and Leningrad, now St. Petersburg. And he was interested in, this is the curiosity-driven part of the work, but he was interested in understanding the color in stained glass windows. So it was already known that the red color is due to gold particles. Really tiny gold particles don't look like gold, they look red. And Faraday, it's a plasmonic effect, it's a metal effect, it's a scattering of light through these metal particles. And Faraday knew this back in the 1780s. You can still see the gold solutions, Faraday's gold solution, in the Cavendish Museum, Cambridge in the UK. But what about the other colors? And Ekimov figured out that that by taking glass, silica, and just adding a couple elements to it, like cadmium and sulfur, or cadmium and selenium, or copper and chlorine, and processing it under different conditions, he would get different colors. He used small angle X-ray. Using small angle X-ray, you can get an idea of the size of the particles on average. And from that, he was able to correlate the size of the particles that he was making with the color that he was seeing. He was surrounded by physicists who were deep into studying something called quantum wells at the time, which is very thin sheets of semiconductors that also show a quantum size effect, where the electron gets confined in one dimension. And so he was inspired by what was going on around him and was able then to explain this phenomenon that he was seeing as a quantum effect. And he wrote a paper in the Soviet literature with the first 3 words, quantum size effect, blah, blah, blah. Independently, and at the same time, Bruce was working in the US at Bell Laboratories in New Jersey. His interest was in understanding how fast an electron can be transferred from a semiconductor to a molecule in solution to do electrochemistry or photoelectrochemistry. This was at the time of the oil embargo in the 1970s under the Carter administration. And people wanted to make fuel out of sunlight, kind of like what we want to do today, for different reasons for today. And so he wanted to understand very fundamentally, if you take sunlight, you create these excited electrons in the semiconductor, how fast does the electron get through the interface to do chemistry in solution to create fuels? And as I said at the beginning, new technologies sort of trigger the ability to do certain experiments. So the new technology that he was using was picosecond lasers that had pulse width of the picosecond time scale, which would allow him to watch the kinetics of that electron going through that interface. And in order to get better signal to noise, he needed to have as much interface as possible. So he wanted his surface to volume ratio to be as large as possible. That meant making the particles smaller and smaller. And so he got to a regime where every time he made a sample, the solution, this was now solution chemistry as opposed to gas chemistry, the solution had a different spectrum, a different color. And he thought maybe he was a bad experimentalist, but he had it available to him at Bell Labs in the late 70s, new generations of electron microscopes, TEMs, which allowed him to actually see what he was making. And then he was able then to correlate the average size to the color that he was seeing. And wrote a paper in 1983 with the first 3 words, quantum size effect. Right? They didn't know about each other. A few years later, actually many years later, maybe 6, 7 years later, Lewis found the translated paper from Russian and wrote Alexei a letter, I'm sure it was handwritten, to say, it looks like we're working on the same thing. We should discuss as scientists that we want to do. And that letter didn't make it directly to Ekimov, it made a little detour through the local KGB office. And Sasha Eckfels, who was a theorist working with Ekimov, tells a story of how, their supervisors came with a couple of KGB agents one day. What's going on? So the KGB was very interested in understanding why an American scientist would write a letter to a Soviet scientist. And why was it so interesting? Ekimov eventually came to the US after the fall of the Berlin Wall. Okay, so that's their contribution. They discovered the effect. And for about 10 years, while I was a postdoc there, Paulo Rosados, who's now president of the University of Chicago, was a postdoc before me. Lewis created a group to try to make the samples better, because you could see in the electron microscope that the particles were all misshapen. They were mostly amorphous. They weren't good enough to really study the fundamental physics of the material. We needed the microscope to tie it up. So we spent a lot of effort. And the reason why it was the case is because the initial samples were made under dry ice temperatures to try to prevent the crystals from going too fast, so they would stay as small particles. And it was made in water. And if you know anything about semiconductors, the growth of semiconductor synthesis, you really don't want any water around. Because what happens is you make oxide, especially if you have a nanometer-sized particle and you put it in water. Pretty soon you're going to have cadmium oxide. You're not going to have cadmium cyanide. And if you want your semiconductor to be crystalline, you probably don't want to grow it at liquid isopropanol, like dry ice temperature. You want to heat it up a little bit. So when I came as a postdoc, already the idea that we had to go to higher temperatures to get better crystallinity was there. And I came in as a spectroscopist. I didn't know anything about chemistry. But there was an inorganic chemist, Mike Steigerwald, who was there. We were using his lab, who taught me everything I know about inorganic chemistry. And I didn't know what a Lewis base was. You can ask a chemist, they don't know what a Lewis base is. And what they had known that was by taking really tiny by taking particles grown in water and dispersing them in a purity which is Lewis base, they could get the crystalline unity to be a bit better. So I asked Mike Steigerwald, okay, what's a Lewis base? Showing my ignorance. And he said, yes, it's got a couple of electrons that can donate into metal on the surface. Yeah, I understand that. And so I said, what kind of Lewis bases do you have in your lab? And so, showed me all these Lewis bases, phosphines and amines and all that stuff. And I tried to understand how this annealing process was happening. And so I got a bunch of Lewis bases when I was trying to do a phosphine. About 20 flasks going, trying to understand the kinetics of how the annealing was happening, at a little higher temperature. And one of the flasks, the particle started to grow. And this beautiful color appeared, and I took an X-ray diffraction, and it was really crystalline. It was this beautiful sample. And for the first time, we could actually start to see emission coming out of this. Before, we didn't see any emission because it was full of defects. Nothing was, the electron wave was finding a defect and losing its energy through non-radiative means. So, I got a sample and I started to do physics on it, and it was interesting. But it didn't happen all the time. It happened some of the time that this magic growth would happen. And then I went skiing over Christmas, 1988 actually. And I came back, I had mostly run out of this bottle of tribrylphosphine. And then I came back, bought 10 new bottles, and started cooking, to make more samples, and it didn't work. It just didn't work. Because accidentally what had happened is I had used an old bottle. And about a third of the phosphine had oxidized. It was actually a mixture of phosphine and phosphine oxide. And I didn't realize it until we did an NMR spectrum of the leftovers in the bottle. And then I bought the oxide and everything started to work somewhat again. Sometimes it didn't work, sometimes it worked, but I got enough sample to do some nice physics experiments. Then I came to MIT, set up my lab July of 1990, before my students came, and I had, my proposal was to study all this physics. The curiosity-driven part of the work that I was proposing was to understand the evolution of properties as you go from atoms to the bulk. The properties of a silicon atom are nothing like the properties of bulk silicon. What happens in between? How do you build up these collective properties? How big do you have to have the crystal in order to see the kinds of semiconductor properties that you would use in a circuit? How small do they break down? So there are all sorts of properties to a material, and they will all evolve at a different rate depending on the size, depending on how big the thing has to be. That was what I wanted to study. And I thought my DevOps preparation would be good enough. So I came to MIT in July of 1990, and I tried to make samples, and it didn't work. And for 3 months until my first students came, I tried to make samples, and it didn't work. And I was watching my career sort of begin to evaporate. Then my first students came, Chris Murray, David Norris, Noel, and I put him to work. You know, and the wonderful thing about first-year graduate students is that they haven't experienced failure quite yet. And they're bright, bushy-tailed, you know, they're willing to do anything, and they're motivated and excited. And so they started to play around, and they couldn't get anything to work. But so we realized we had a proof of concept that one preparation had worked. How do we reproduce it? You know, what were the elements of success for that? So the elements of success was that it was done at high temperature or higher temperature with crystal. The annealing was done under nitrogen. So, you know, we realized very quickly that we had to get rid of the water part of the thing. So we re-engineered the synthesis, all using organometallic precursors, all under nitrogen, as high a temperature as we could. And if you want to make particles that are all the same size, what we realized is we need to have a process that separated the nucleation from the growth of the particles. We had to create little tiny seeds and then grow on top of the seeds. That was a concept that was an old concept. It was known, you know, for 40 years before I arrived at MIT. But it hadn't really been applied to nanometer-sized particles. It had been applied to much bigger particles. For instance, applied to the emulsions in photography, the silver halide emulsions in photography. So we took those things together, and you know, as many things, the devil is in the details. You know, the concept is very simple: nucleation and growth, high temperature, no water. Right? You got to actually put it together with the right chemicals, right? And so that's what we did, and we wrote a paper in 1993. And that was my first paper at MIT as an assistant professor, and eventually that's what the Nobel Committee gave the prize for the synthesis part. So here's Chris Murray, like a young, now Chris is a professor at Penn, David is a professor at ETH in Zurich. They don't look quite like this anymore. I don't look alike, but I look like them. And this is where our simple flask, right? Now it's called the hot injection method. We have nano-organic precursors that are stable at room temperature, a solution of a solvent. We quickly inject that into a coordinating solvent with some ligands that coordinate to the surface of this crystal as it grows to prevent it from growing too fast. Kind of like the idea that Lewis had to go to a really low temperature to prevent the particle from growing too fast. 300 degrees Celsius. We can watch it with our eyes because we're looking at color. When it has the size that we want, we just turn the heat off for rest to grow. A video of what it looks like here. So there's the precursors in the syringe. The flask is at 300 degrees Celsius. Quick injection. The color that you see is from nanometer-sized seeds of cadmium-selenide at high temperature. So quick seeding. Once the concentration has gone to below a certain level, you can't nucleate anymore. The only thing you can do is grow. And so I'll spare you the 20 minutes of growth here. They're now it's much darker because they become bigger. The student is still taking samples out as the growth occurs. Then you can see then the change in color from the beginning of the reaction to later on as the particle size grows, this homogeneous sort of growth of the particles, with the small particles looking more yellow because they don't absorb as much of the visible light, and the bigger particles looking redder. So more of the visible light, you put a UV lamp on this, and now you're creating these single electrons, waves, and then you can see the light coming out. So this is like the organ pipes, except now with electrons instead of sound waves. And so we wrote a paper, as I mentioned, in 1993. And there's a few words that I underlined here that are important. It was simple. It was a single reaction. And we had a way to purify the material. And that's what we intended the size method of precipitation, a simple thing. Those words turned out to be important for the commercialization, for the technology aspect. Because if you make anything, the cost of making anything is proportional to the number of steps it takes to make it. You know, if it's a computer chip, the more steps, the more expensive that chip is going to be. If it's a car, the more parts it has in it, the more steps to assemble it, the more expensive it's going to be. A pharmaceutical compound, the more complicated it is, the more steps, the more expensive it is to make. And so this was simple. So this turned out to be important for creating something that was not too expensive. And then because we were chemists, we knew we had to purify what we had. And we had this size-selective precipitation, which was a simple way of cleaning the particles or removing all the side products and unreacted precursors from the solution, so that we can then create what was basically the equivalent of a molecular, very large molecules in solution that were now the components. So that invention created, so before that, you know, so this is 1993, the discovery was 1983, so there's been 10 years between the discovery and the synthesis. Once we had the synthesis, then it became accessible. And before there was a very tiny community of people interested in this because the material was really not really good. But once we had good material, a lot of people started to be interested in the field. And the community started to grow. And once you have the community growing, you have more people working in the field, then progress begins to happen faster and faster. For us, being able to make these samples allowed us to do some physics and to see things that we couldn't see before. For instance, this is an optical spectrum. This is the absorption spectrum. We could see these extra peaks in the absorption spectrum. So this is the wave, the electron wave, and these are the harmonics of that wave. Right? Just like in the sound wave, or if you pluck a guitar string, you know there are harmonics, the higher pitch harmonics. So these are the harmonics, the excited states of the particle in a box. And Chris, in his thesis, has this progression of spectra. So this is blue here, and this is red here. These are tiny 1 nanometer particles, and as you grow the particles, they march across the visible as they get bigger and bigger, and the energy of the wave gets smaller and smaller. And this is the bulk sitting right here, right down at the bulk. By the time we're at 15 nanometers in size, you're basically something that looks, with this experiment, it looks like a bulk. And the fluorescence, the light, the color of the light that came out was very narrow, fairly narrow, I should say, fairly narrow. And I thought it was incredibly bright. The quantum yield, the efficiency of the light coming out was about 20%. So about 20% of the photons, the blue photons, were converted into photons of that particular color. And I was so excited, because it was so bright. Because before it was 0%. From 0 to 20 is a huge advance. And one of my colleagues in Germany who was working in a quantum lab told me, 20%. It means that 80% of your sample is crap. Yeah, he was right. But what this not so great material still allowed us to do was to do some physics. So we went to low temperature, 10 Kelvin here. And I told you these were the harmonics. And we wanted to know, how do these harmonics actually evolve as a function of size? We can see the lowest wave, but what about the higher waves? And on this graph here, these are the small sizes. These are big sizes. And these are the energies of the harmonic. This is the energy of the lowest state, that's one state right here. This is the next step up, so that would be this second peak here. And as you increase the size of the particle, you go from the small quantum dots eventually perhaps to the bulk, then you see the harmonics coming together. And in this area here, they're coming together kind of uniformly. Then you get to a size regime. Whoops. Right around here, where weird things happen. Weird things happen because the box is not empty. The box is full of atoms. And this one electron interacts with the atoms. And interacts with the atoms in a way that we understand from the bulk, from the bulk semiconductor. That interaction creates all sorts of interesting band structures and stuff like this. And so that's the beginning of the band structure of the semiconductor coming into play right here. There's enough atoms in the box that the collective properties become like those of the bulk semiconductor. Before that, we didn't have enough atoms in the box. And as a spectroscopist, we call that an Border crossing. Two states that try to cross each other, but if they're interacting with each other, they can't cross. And when you're a spectroscopist and you see that, it's like manna from heaven. You know you're learning something fundamental. So we did a lot of good physics. We're still doing good physics. That was 1995, this was published, so very soon after the synthesis. 1996, people realized, us included, that you could further protect the quantum dots from its surrounding by growing shells of other materials, other semiconductors, making a core shell structure at the high, using the high temperature. So everything was well controlled. So all these papers came out at the same time, making these core shell structures. And that's when the quantum yield went up from 20% to, at the time it was about 50, 60%. Today, quantum yields are 100% using this core shell structure. So now you can make these solutions that are really truly bright, huge quantum yields. And that was around the same time that Nakamura had discovered how to make gallium nitride diodes, blue diodes in the mid-90s, late 90s. So that was hugely inspirational for us because now we had a material with an absorption that went all the way from wherever it was going to fluoresce into the blue, unlike dye molecules, which only absorb close to where it fluoresces. So with one wavelength, 465, let's say, from a blue diode, we could excite and create that single electron wave into make all these colors at the same time. So that gave us all as a community the idea, well, maybe we could use these things for something. Maybe they would be useful for multiplexing. Maybe they would be useful for anti-counterfeit. You could put them in an ink and watch the light coming out. That turned out to be a really hard application because, not because the thing doesn't work, but it's a very tough market to crack. And the first application that used this idea of using a blue light to multiplex and see many things at once, using color as a tag, because we were chemists, that was biology. People were using dye molecules to fluorescently tag cells already, using dye molecules, but dye molecules have this, they were great. I don't know if really bring dye molecules, but they have a tendency to photobleach. So if you shine light on the dye molecule that or a cell that's been tagged for a long time, that the light will slowly fade out. Because you're breaking carbon-carbon bonds. The quantum dots were pieces of rock, three-dimensionally bonded. They shouldn't have this problem. And also, you can't really easily multiplex with dye molecules the way they do. So a bunch of us started working on this in the 1997. Keeping track of time. 83 was the discovery, 93 was the synthesis, where suddenly becomes accessible. 3 years later, 96 was the core shell, really bright. 97, we start working on biology. 98 is the creation of the first company, the solid dots. I went ahead of myself because I want to show you another little piece of physics very quickly. So once you have the core shells and you have stability, and they're really bright, now you can go look at them one at a time. And when you do that, you find that the particles, these are single quantum dots that you're looking in the microscope now, that they're all stable, they blink on and off. So, and if you go to low temperature, you start learning about the physics of them in a way you couldn't before, in a way that was hidden by the fact you still had an inhomogeneous distribution of stuff. Right? Now you can look at one at a time, and you see things like vibrations, which we call phonons in the solid state. Now you can start to study how vibrations change as a function of study. So going to 4 Kelvin unlocks really interesting physics, and we're still doing that today. It's been a really great ride to study the physics. And I want to go straight now to the application in biology. All right, so 96, 97 was the core shell. 97 was the start of thinking about biology, some proof of concept experiments. 98 was the creation of Quantum Dot Corporation. That was me and Paul Lusados and Shimon Rice from Berkeley. And we had to solve, the company had to solve the problem of how to protect the quantum dots from water. Because, they're still semiconductors. They don't like water. We're trying to put them in a biological environment, trying to put antibodies on them and tag parts of cells. This turned out to be a lot harder than we expected. It's actually a hard process. So 98, the company was started, but they were able to start selling products about a couple of years later. This is an example from the company's, one of the papers from the company. The red nucleus of this cell is tagged with quantum dots. The green is tagged with the dye molecule, and you can see then the photobleaching of the dye. The green disappears because the dye is photobleaching, but the red stays intact because the dots are much more stable. That really showed the stability of the dots as a three-dimensional inorganic material. We did more experiments in more complicated experiments. This is an in vivo experiment here, where we were looking to see if we could identify rare cells in vivo. And in this case here, these are hematopoietic precursor cells that are basically stem cells in the bone marrow of this mouse. And these cells overexpress some receptors that are not there in normal cells. So if you can target these particular receptors, you can color code these rare cells, and you can start studying them in the environment, etc. So we use two colors of dots, red and green, which we target these receptors with. And some cells get targeted with red, some cells get targeted with green, but only the ones that are of interest have the two colors together. Red and green make yellow fluorescence, so you go with a microscope and you look for yellow. And there's that single cell there, and then you can start to study it in real time. You can start to study its microenvironment. Is it oxygen rich? Is it oxygen poor? What kind of metabolites? Is it acidic, etc.? You can start to learn biology. This was a hard experiment. Then we thought, maybe there's some easier things we can do in biology with this. One of the things that was easier was to realize that we can make quantum dots that emit in the near infrared or the short wave infrared, beyond the silicon. You can see in the 1 to 2 micron range. And the advantage of going to that wavelength range was twofold. One was that there's a lot less scattering. The longer the wavelength of the light, the less scattering you have, so you can penetrate deeper in tissue. And second, organic material really doesn't fluoresce in that wavelength range. It's completely dark. It likes to fluoresce in the visible. So if you have a visible emitter, you can have a lot of background fluorescence. It's hard to see things. But in the shortwave infrared, your emitter has a dark background, so you can see things much more clearly. Your signal from is going to be much better. One of the experiments that we did was to look at blood flow in glioblastomas models, mouse models. So this is an experiment which is all done with quantum dots. The red are arteries, the blue, this is a mouse brain here. It's a window model, so the mouse has a little window attached to it. It's running around and it's got glass on it instead of a skull. And it has a tumor growing in its brain. The blue are the veins, and the green is the tumor. How do we get this image? Well, you take a bolus or a quick injection of quantum dots in the vasculature of the mouse. The first thing that shows up are the arteries. So these colors are artificial colors. They're time-stamped colors. The first thing we see are the arteries. We wait a little bit longer. Then we see the veins. Color that blue. And then if we wait a long time, the quantum dots are cleared out of the circulatory system through the kidneys. they don't clear out of the tumor as quickly. So you can wait until the blood is, they're gone from the free-flowing blood, and then you can just know then where the tumor is. Before that happens, we can go in, create a different kind of particle. These are now composite particles, that are about 100 nanometers in size. They're big enough that we can see them individually in the microscope at room temperature. And then we can follow these particles in the blood, these bigger particles in the blood. What you see then, in the tumor area, so these big, bright objects, that's the 100 nanometer indium arsenide particles, they're glowing around 1.3 micron. And you see that the flow of blood in the tumor is, compared to the flow of blood in the normal brain tissue, is completely different. Right? There's weird flow that it's going back and forth. It's not flowing in one direction. And visually, this tells you why it's so hard to deliver therapeutics to tumor. Right? You can't get it in there. The flow is not doing it. And our collaborators at Mass General Hospital, their interest was to develop therapeutics that would make this flow look like that, so that it would improve therapies. And you could have the best molecular compound to treat tumor, but if it doesn't get there, it's useless. So all that delivered. So this was a lot of fun. But it was very clear also that it was a tool to learn biology. It's a fun tool to learn biology. It's part of Fillmore Fisher's catalog. But it wasn't going to go into humans. I was interested in going to humans. Eventually I did, using a different kind of technology that doesn't have quantum dots. Use what I learned from quantum dots to create something that could go into humans. In the early 2000s, we started making friends with electrical engineers. And that's where the real big application, the money-making application, the widespread application came about. There were two companies that were started, Nanosys and Quantum Computer Vision. My students were part of both of these companies. Computer Vision was straight out of MIT with two of our students from MIT. Nanosys was many people from many universities together. Both are now part of much bigger companies. And the first product that came out, it's the same idea as in biology. You use blue light, and you get a different color out when the dot is also blue light. You downshift. You convert the color from one to another. That's great for lighting, right? And so these blue light-driven LED light bulbs were just starting to be commercial at the time. This is 2010. So this was a product from Computer Vision. These light bulbs were very expensive, right? It cost $100 a piece. And there was too much blue light in them. There wasn't enough red. So if you use these light bulbs in your bathroom in the morning, you brush your teeth, and then you look at yourself and you want to go back to bed because you look like a ghost, right? But if you took quantum dots that absorb blue and re-emitting red, you could put back some of that red. You could make the light warmer and create a much better color spectrum. And so that was sold for on the market for a while. But the light bulbs started to fall down in price. And something that you could make money from by adding a little piece to it, when it's $100, is okay. But when it's $10, you don't make any money anymore. Right? It's too inexpensive. And so that wasn't the right technology either to really break into something widespread. But the same idea could be used for different technology, for different items. And those were screens, TV screens, and eventually laptops and other kinds of display screens. So around that time, the way that displays or LCD televisions work is that you had a light source that was based on these blue diodes with a phosphor on top to make white light. Then you had white light in the back plane, and then you would have filters to filter out red, green, and blue light. Those were your RGB pixels, and then you have your polarizers to turn them on and off. if instead of the phosphor to create white light, we use quantum dots to create pure green and pure red. So now we have pure green, pure red, and pure blue. This should be more energy efficient because we don't have all these colors that are all filtering out, and it should be then the manufacturers would be able to have better color saturated displays. That was a good idea, it turned out. QD Vision was the company that provided these parts. The first company to make them was Sony, 2012. And they created these televisions. They were based on Fasson. I was so surprised when they put Cadmium in their consumer products. Because I had been talking to Sony for 10 years before then, and they had a list of elements that were forbidden. And cadmium was on the list of forbidden elements. And here they were putting cadmium in there. So, whoa! Because it really worked, right? But the startup company, QD Vision, wasn't able to scale up fast enough from a few parts to millions and millions of parts. And so we dropped the line. But Samsung was, watching this, thought this is a great idea. Cadmium is a terrible idea. So they put a lot of money, a lot of time in creating the same quantum dots, but with indium and phosphorus, indium phosphide. And they were willing to be patient. And they came out with their model, the QLED model, 2015. And they called them QLED TVs. They bought QD Vision, and the real reason why they bought QD Vision, because Samsung can do anything they want. They don't really care about much in terms of IP, but they cared about this little ball right here. That was a trademark. And so that's really why they bought QD Vision. Because if you get rid of that, that's OLED. And LG had the market for OLED TVs. And now Samsung could say, oh, we need better than that. We've got QLED. Today, the product that is there is a combination of OLED and quantum dots. It's these screens where you create little OLED pixels that only emit blue. So you have blue emitting OLED pixels, you can address them visually, create blacks, and then you inkjet print on top, red, green, quantum dots. Now you have pixels that are red, pixels that are green, pixels that are blue, individual addressed. You have, and you can drive it really hard. You can make it really bright. And the day of the Nobel Prize, I got an email from Samsung Electronics asking me, where did I want my new TV delivered? And new TV OLED TV. I said, give me the biggest one and deliver it to my office. So a week later, I had this beautiful television, and I was really amazed how bright it was, compared to the previous generations. It's so bright. And, on per square inch, it uses a lot less electricity than the previous models. But because, what do we do as humans, when we say that, when we create something that's more energy efficient, we make it bigger and brighter. So these are amazing, but they use up a lot of electricity. So I have one more example of a technology, which is, this is an idea of using night vision. So if you have a night vision camera, it uses indium arsenide as a semiconductor sensor. It sees from 1 to 2 microns really well, but it really doesn't see the UV well at all. So if you want to have something that sees all the way from the UV to the 2 micron, you need a lot of cameras. You need 3 cameras, probably a UV camera, a silicon camera, and an in-glass camera. But we have a very simple fix if you want to see UV with an in-gas camera, which is to put a thin layer of quantum dots that absorb the UV, that really emit light at 1.3 micron, absorb strongly in the UV. At 1.3 micron, you can have it so dilute that it hardly shadows. It doesn't really affect the efficiency of the camera. Right? Maybe you put it right at the edge of the camera. And then you can sensitize it to the UV. My students who were working on this, this was a collaboration with Raytheon, they had fun with this. They created this in the video, thinking of maybe, a scene in the 1960s in Berlin, maybe. You got some spies that are trading secret documents. You get a third spy that's trying to track briefcase with a secret document, and he's put a UV tracker on it. So you can't see the UV with your eyes, but with the quantum dots, you can see the UV. And this is happening at night in the cafe. So he's got this night vision camera, and he wants to make sure that he's tracking the right suitcase. Right? And so this part of the sensor is coated with thin film of quantum dots, and this part is no quantum dots in this night vision. So the camera here, and so Frank here is going to get up. He's going to pick up the briefcase. There's the one not tracked behind, walking across. And as soon as you get to the part of the detector that doesn't have quantum dots, it's blind to the UV. Right? Simple fix. Right? This whole idea of downshifting light, if you got the right material, you really can do a lot of things. Okay, so a lot of different applications still to come. You know, we can do electroluminescence. So this is without the blue light. This is just like OLED. This is a technology that most of the display companies are working on, hoping that in 3 years or so they'll be able to use quantum dots instead of organic molecules. There's night vision cameras using quantum dots. A bunch of startups are trying that out. And for solar energy harvesting, where I am with basically a pair of sunglasses coated with dots that capture light. So what did we create? What is it today that we have? We have a lot of different materials that can be made and that are very well characterized in the same way that we characterize the quantum dots. A lot of different morphologies. The core shell is just one, but today we can make bras, we can make all sorts of interesting things that all have weird properties. You can combine them together. Applications, real applications come out, like in displays, and lighting, biomedical imaging, light sensing, solar energy is one that there's a few startups that are selling products in that way. The ones that are coming, I'm pretty sure, are going to have to do with catalysis and photocatalysis, back to what Lewis was trying to do to create solar fuels. Electronics, as an ink for electronics, an ink for optics, and then quantum system, quantum remission, qubits, that kind of deal. That's what I'm interested in now, is that last part right here. I've had a lot of students in my years, about 150 students. And we had a reunion in May, and it was really fun to have everybody there at MIT. It's not showing up. Yeah. And all of these people cost a lot of money. So I want to thank all the sponsors, and I want to point out that the innovation part of the work, the discovery of the synthesis, was all funded by internal money. My MIT startup foundation money, because we didn't have anything to show to the funding agencies. All we could say was, I think I'm going to make a recipe to make really great dots, and I'm going to study the physics. What reviewer was going to say, okay, give them $300,000. Once we had proof of concept, then we can do it myself, which I did in 1991, soon after I had some proof of concept. And a lot of the resources that I had from the first 10, 15 years, was all from these government agencies. DOE has been incredibly generous to me over the years. ONR, the Army, NIH, all the biology centers under the NIH one. Incredibly important to have those resources around. Maybe they don't get the innovation quite right, but they get the growth of the science. They get that right. And once you have something that looks like it's commercial, then suddenly the bigger companies become interested. And so today, I would say that about 60, 70% of my funding comes from that part of from the Samsungs and the First Solars of the world, and the government is about 30%. Okay, thank you.
So we have time for a couple of questions. There's a microphone back there. If anybody has a question, please raise your hand. I see 2 questions right up here.
Before I answer my question, I just wanted to thank you for the presentation. It was very, very good and very fun to hear about the applications of quantum dots. But my question was, you were talking about that there's colloidal cases for the quantum dots. How do you synthesize them, and what are they made of?
Okay, so the word colloidal just means that they're floating in solution. So what I showed you was all colloidal quantum dots. We just use the word colloidal to mean that they're growing in solution and they're dispersed in solution. And maybe it's a little misnomer, but that's what it feels like, colloidal quantum dots. And as opposed to the quantum dots that physicists may have very pristine conditions.
Beautiful talk, Dr. Bawendi. My question is more of a fundamental one from the start of your presentation, where you introduced the method of introducing an electron, a free electron, into the quantum dot. I was wondering, you're hitting that quantum dot with a stream of photons. How do you make sure that it's just one free electron that is excited within that quantum dot?
So the stream of photons that we use is actually not very strong, right? So you've got many quantum dots around. Every now and then, a quantum dot absorbs a photon, liberates an electron, and that electron then sees the hole in its side, or electron will go to the hole. The time that it takes for that electron to find the hole is on the order of nanoseconds. A second photon coming in, that's going to be a few microseconds later. So we never really have two electrons liberated. Under those conditions, we can make conditions where we have two, but not under those conditions.
Great talk. I have a question that as the fraction of atoms sitting on the surface increases as the quantum dot size
That's small.
decreases.
Yeah.
At 6 nanometer, like 50% of the atoms, you don't know what they are doing. How can you comment how to handle them?
Yeah, so the surface has always been something that, so it used to be that anytime we didn't understand something, we'd say, oh, it's the surface. Yeah. Weird optical features, it's the surface. Until we realized that it wasn't the surface, because once you passivate that surface, you remove the defects on the surface. You find out that those, for this particular material, the surface atoms actually are part of the electronic properties of the ball. The defects are, if any, of the surface bands are inside the band, inside the convection of the band. They're higher energy than that wave that creates for the electron. So the surface isn't really that important for us electronically.
Thank you so much for the wonderful presentation, and I'm going to follow up on Jay's question. When you make a core shell particle, how do you select the shell such that the symmetry in band gap does not interfere with the quantum phenomena you're looking for? Because of the
If you look at the band gap of the quantum dot, let's see, this is the valence inflection band. You look for a shell that's like what we call a type 1 semiconductor, where the convection band and valence band of the shell are spaced like this. Right? The band offset is such that it goes like this.
Other questions?
What led your thinking, or what was involved in your thinking when you're in the presentation? You were in your MIT laboratory or Bell Laboratories working with these various crystals, and all of a sudden you're working with cadmium selenide and cadmium sulfide. What was the leap of logic to go to that material?
The cadmium selenide?
Yes.
Yeah, so that's a good question. So when Lewis started out, he was using cadmium sulfide, where all the colors, it's actually hard to see because the band gap is in the yellow, and then it just, you hardly see any colors. But cadmium selenide, you can see everything with your eyes. It's invisible. It's the most wonderful material.
How did you know to go to that material?
The chemistry was easier than cadmium sulfide. It's totally practical, right? But once you hit that, you realize I can see everything by eye. I don't need a spectrometer. I can just see it.
Are there any other questions?
Hi. So thank you so much for the presentation. You mentioned that electron microscopy is really important for nanoparticle science. But were there any other types of spectroscopy that you tried out, and what did you learn from that?
We've tried, a lot of different methods, like XAFs, UPS, XPS, leads. You name them, and we probably tried to learn something using those methods. I showed them the optical methods are what we do all the time. The characterization methods, we try everything we can. So you probably need to.
Yeah. Okay, well, thank you, everybody, for coming. Let's give Professor Bawendi a thank you.